Hello, a great welcome to this series on PLAXIS. Myself is Jarajan P. This is tutorial number 10 and it will demonstrate the lateral load analysis of a pile using the geotechnical software PLAXIS. PLAXIS has two approaches for the analysis of piles. One is known as a volume pile approach and the other known as the embedded pile feature. So in this tutorial we will consider the volume pile approach, and in the next tutorial, that is tutorial number 11, we will discuss about how to model the same problem using the embedded pile feature. So let us straight away go to the problem statement. So for the analysis we consider a soil domain of a size 25 meter by 25 meter and of a depth 25 meters. So the pile that we use is of diameter 0.6 meters and length 12 meters, and the water table is considered to 1.5 meter below the ground surface. And for the modeling of soil, we use the material model as the popularly known Moore-Colombo failure criteria, and the drainage type will be the drained, and we'll use the strength parameters. For example, C will be used as 12 kN per meter square, Phi will be 30 degrees, and direction angle of 0 degree. As the pile in this tutorial will be modeled using the volume pile, we need to specify the properties of the pile material. For example, here we'll use the material model as a linear elastic, and the E value will be taken as 2.5 into 10 raised to 7 kN per meter square. And the length of the pile, as already discussed, is 12 meters. So in this tutorial, we'll apply a horizontal load of 800 kN at the pile tip, and we will investigate how to obtain the variation of the bending moment, the variation of the soil resistance along the pile depth. And this applied load of 800 kN corresponds to a stress load of 2830, which is simply obtained by dividing this load by the cross-section area. Now, the PLAXIS version, which I am currently having, do not have the capability to extract the bending moments along the pile length. So, based on my structural knowledge, what I did is I have modeled a slender beam element along the center axis of this pile, so that the modeled slender beam element will follow the deformation profile of the pile, and then I will extract the beam deformation, the beam bending moment, the beam reactions, everything, and then I will scale up in order to obtain the actual variation of the bending moment, shear force, and the deformation along the pile length. So for this beam inside the volume pile, I have considered the same area of the pile element, that is 0.2827 meters square, but the Young's modulus or the tangent modulus used for the material will be very less, that is 25 only, and the moment of inertia will be 0.00636 meter raised to 4. So let us just start the PLAXIS. Okay, so let us just start with the title. So we'll call it as a lateral loaded pile. Now let us define the model boundaries. We know that the model is of 25 meters by 25 meters size in plan, so we'll set it as minus 12.5. And similarly for the y also we'll set it as minus 12.5 plus 12.5. That's okay, fine. So let us define the stratigraphy. We will insert a borehole at 0, 0, 0. So let us start define the layers. We have got only a single layer, so just add it, and we know that the bottom will correspond to minus 25. Okay, and regarding the head, we assume that the water table will be at 1.5 meters below the ground surface. Accordingly, we'll keep it as a minus 1.5. So that's okay for us. Now, regarding the materials, as you can see that in order to save the time, I have defined all the two materials already under the soil and interfaces, and one is the soil property, that's a C5 soil, and the second one is the pipe property. Let me just edit it and show you. So here, as you can see that this is my C5 soil and some more failure criteria we have used. And regarding the parameters, we have got the value of 8000 kilonewton per meter square, and the C is equal to 12 and 5 equal to 30 degrees. And regarding the interface coefficient, it R into is assumed as a 0.60, so that's okay. And now let me just show you the pile properties. And the pile is considered as a linear elastic material with a non-porous behavior, and the gamma is used as 25 kN per meter cube. And regarding the tangent modulus, we have used 25 into e raised to 6, that is kilometer per meter square with a Poisson ratio of 0.20. And now coming to the other parameter, that is we have defined the two properties, that is the soil as a pile. I have defined one more property under the head beams, and as already discussed earlier, this corresponds to the beam that is embedded along the central axis of the pile in order to extract the bending moment, deflection, etc. You may just edit it, and as you can see that this is defined under the head beam, and we have defined an area of 0.2827 meters square that corresponds to a pile diameter of 0.6 meters, and gamma is taken as 25 kN per meter cube, and the linear property is assumed, or the linear response is assumed, that is E is equal to 25 kN per meter square. As you can see that the value of E assumed is very small to make it very flexible, and I3 is equal to I2, that is taken as 6.36 into E raised to minus 3 meter raised to 4. So that's all regarding the material. So let us assign the soil material that's already defined. So we'll go to the soil 1, you can just select the material, that's a C5 soil. So you can see that yes, the color is changed in order to reflect the material assignment to the soil. So now we are ready to proceed to the structures mode, or the structures module. And the structures mode, first of all, we need to develop the volume pile that is of diameter 0.6 meters and length 12 meters. So let us start straight away by defining the polycurve. So let us define a polycurve. For example, I will create it at the center, and the segments, I will add a new segment, and here I will select the arc, and the right angle I will choose it as 90 degrees, and the radius, we know that is the diameter is 0.6 meters, so this will be 0.3 meters, and the segment angle is a full circle, so this will be 360 degrees, and the displacement angle I will keep the same. So now going to the general, I want to just adjust this to 0.30. Let me see, 0.30, that must be good enough for me. Okay, so let me just zoom it so that you'll be able to see the. Okay, fine. So we have, as you can see that we have defined a circle that represents the periphery of the pile. So if you double click it, you will find that okay, in the segments you will find that you want to just see the properties, you can see that that is having a radius of 0.3 meters, hence it represents a pile of diameter 0.6 meters. Okay, so now let us start creating a surface out of this polycurve. Just right click it, you can just create the surface. After creating the surface, what you can do is we can just delete the polycurve. So just delete it. Okay, so now what we can do is we can extrude this surface uh, till the pile bottom, that is till up to a level of minus 12 meters. So we just select it, put the extrusion, and we know that the bottom of the pile that corresponds to minus 12 meters, so minus 12. So apply. Okay, fine. So we have created a pile out of this surface by doing the extrusion. So let us delete the top surface again. Okay, I will delete it. And then let us decompose this into the various surfaces, because we want to define an interface. We want to apply a load across the cross section. So you can just decompose into surfaces. So now having done that, you can say that yes, now a side surface face volume is available to us for the definition of the interface. Now I want to delete the bottom surface because that is of no use for me. So let me just go to the bottom. So just select this bottom surface and delete it because we don't require this. Okay, fine. So this means that we have generated the pile. Now having generated the pile, the next job is that we need to create an interface that will adequately represent the pile surface to the soil interaction. So Let us just select the surface, that's a side surface. Just right click it, and you can see that yes, there is an option code known as a positive interface. Okay, so we have defined the positive interface also. Let us now proceed to define the beam element that is aligned along the center axis of the pile. Please remember that the intent of modeling this beam element is to extract the variation of the pile deformation as well as the many moments along the pile length. So we'll do this by clicking this by create beam. So I will create a beam element from one point to another and just go on editing the coordinates. So this is the starting point and then my end point will be the same, but only difference is that my z coordinate it will be minus 12, minus 12. That is the bottom of the pile, and the material that is assigned. So I will call it as a beam inside. The material is already defined by us. So this means that yes, the definition of the beam along the center axis of this volume pile is complete. If you don't want to monitor, for example, the bending moment along the volume pile, this beam definition may not be required. So now we can go to the next stage, that is applying the traction along the pile surface. So this can be done straight away by applying a surface load on the top. So you can just go over here, create a surface load. So you can see that by default, PLAXIS has created a surface load, and that is a -1 kN per meter square downwards. Obviously, we will change this while going to the staged construction mode. So this means we have almost completed the definition of all the items required under the structures mode, and we are ready to proceed to the mesh mode. Now in the mesh mode, I want to be very specific. As this is only a tutorial, I'm not going to define any kind of a refinement zone around the pile. Please remember that the accuracy of the results obtained from a volume pile analysis is heavily dependent on the mesh analysis. So for all the practical problems, it is important that you define a well-defined refinement zone around the volume pile, and the size of this refinement zone, many recommended criteria are available in the literature, and also you can define the size based on a number of trials so that you will arrive at accurate results. So for this tutorial, we will not go for any kind of a mesh refinement zone. We'll straight away go for the element distribution of medium, and will allow the PLAXIS to generate the meshing accordingly. Now, here I want to specify one more point. In the next tutorial, we'll be defining the same problem, but we'll be using an what we call as an embedded pile feature available in PLAXIS. If one is interested in comparing the results from these two, that is from the volume pile approach and the embedded pile approach, please ensure that the mesh sizes are comparable. Okay, then only we'll be able to compare the results properly and come to a valid conclusion. So now let's quickly see the meshes that is generated by the PLAXIS. So yes, you can see that this is the mesh that is generated by PLAXIS. Fine, we don't have any kind of a refinements on in and around the pile. So this means that we are now ready for the staged construction. But before going to the staged construction, let us select a point also. So we'll search processed, and in order to monitor the response, we'll select a point that is at the origin 000. So we'll update. This means that we are now ready to proceed to the staged construction, where we will start defining the various important phases of the construction and defining, for example, the materials, defining the surface attraction on the pile, all those things, and then we'll perform the calculations. Now in the staged construction, I have defined the three phases earlier. That is, the purpose is to save the time, obviously. So let me just explain the three phases that we have defined. Obviously, the first one is the default initial phase created by PLAXIS. And if we have asked PLAXIS to compute the self-weight stresses inside the solid mass using the case zero procedure. And now coming to the second phase, that's a pile installation phase. You can see that we start from the initial phase, and the calculation type that is used is the plastic. and all other numerical control parameters are kept by the default. And now coming to the third one, that is a pile loading phase. We started from the pile installation phase, and here we have reset the displacements to 0, and all the numerical control parameters are kept by default because this is a simple problem. We don't require any kind of a refinement. Now let me also show you what are the changes that we have made in the various model components. So going to the initial phase, you'll find that we are kept to only the soils active. Now coming to the next phase, pile installation phase, you'll find that we have made the beams uh, as well as the interfaces active. Okay, and here one important thing is that in the soils we need to define the property of the volume pile, that is defined here. Soil 2 is defined through the material pile, and going to the pile loading, it is exactly same as phase 1. Only difference is that in this case we have defined the surface load. As you can see that this is defined right now as a sigma x, that is a stress load across the cross section, which is equal to 2830 kN per meter square in the x direction. This means that we have defined all the phases properly, and we would like to obtain the response of the pile under an applied load of 800 kN, which corresponds to a stress of 2830 kN per meter square. So having done that, let us proceed for the calculation. Just press the calculate button. Okay, the calculations are complete. Now we are ready to review the results. So as usual, let us start with the initial phase, wherein we will be able to see the initial stresses generated by PLAXIS. So we would like to see the stresses. So go for the Cartesian dot stresses sigma set. As you can see that the stresses increases with the depth as expected, and the maximum value noted down is of the order of minus 448. This is very close to 450 kN per meter square calculated at the bottom. So now let us review the pile response, for which phase 2 is very important to us. Go to the phase 2. Let us proceed for the deformations. We are interested in the total deformation UX because we have applied the load in the x direction. Let me just zoom this top surface in order to show you the variation. So as you can see that this is how the deformation in the x direction changes. As you can see that the deformation is maximum near the pile edge, and it decreases exponentially something away from the pile, right? So you can see that the maximum deformation in the x direction is of the order of, say, for example, 240 mm. Here also it is given here 232 mm. Okay, fine. So now let's just quickly examine the deformation across a particular cross section. Go over here. I'm interested in, for example, minus 30 to plus 30. I just want to see the deflection contour. So this is okay for me. So yes, okay, fine. So this is the deformation response across the central axis, across the central plane. As you can see that yes, the deformations are maximum around along the pile axis, and it decreases away from it. Now if you are interested in seeing the deformation across the cross section, you can just take a quick line cross section. So I would like to take across this section something like this. That's okay for me. Sorry, as you can see that yes, this is the variation of the UX along this pile. So you can say that yes, it is maximum very near to the pile, and it decreases quickly away from the pile. So having done that, let us quickly review the some critical charts. So points that we want to monitor the response to the origin. Let us go for the charts. We'll have a new chart. Sorry. So in the x-axis, we'll choose a multiplier that's a sigma m stage, and we'll choose the point. There's a monitoring point. In the deformation, we'll be choosing it as the UX. That's okay. And here you can just double click it, and you can choose the phase. You're interested in only the phase 2. That's okay. And here I want to just exchange the axis. So it must be okay for me. Yes, as you can see that yes, this is the load deformation curve of the pile. As you can see, the maximum deformation recorded is of the order of say 240 mm when the pile has reached a maximum load of 800 kN in the x direction. So now let us quickly see there's some response in terms of the deformation and the bending moments in the pile. So what I will do is I'll go for I don't record this. So this also let me just okay, this also I don't require. All fine. So here let me first of all select my structure. So I will select the beam where I'm interested in. Okay, so here you can see that it provides us, as I have selected the beam, it provides me the, first of all, this is the deflection along the beam profile, as you can look here. So this is the deformation, the maximum deformation being at the top, and it decreases towards the bottom of the pipe. And as is the beam element, it is also possible for you to obtain the variation of the bending moment. For that, you can go to the forces. You can go to the main moment is M3. Yes, you can see that this is the variation of the bending moment across the pipe. So let me just do something like this. So you can see that yes, the maximum bending moment is of the order of say 1.375 into 10 raised to minus 3. On scaling up, this appears to be 1375 kilonewton meter. So that is all regarding the analysis of the pile in terms of the deformation as well as the bending moment. And I've exported the important data from the PLAXIS onto my Excel in order to show you the final curves. For example, you can see that the P delta curve, it is shown over here, wherein you can see that along the x-axis I have taken the displacement in the x direction, and along the y-axis it is the load. As you can see that when we reach a maximum applied load of 800 kilonewton, the displacement of the control point is sort of say, for example, approximately say 0.24, that's a 240 mm. So this is the overall response of the global behavior of the pile. Now going to the pile moment, you can see that it is a moment diagram that I have extracted from the beam. Obviously, you will find that there's some kind of a localized push-ups over here. Right, as you can see that yes, there's a pile depth. This plots the variation of the minimum across the pile depth. You can see that the coordinate varies from 0 to minus 12, and we observe a maximum bending moment approximately to the tune of say 1400 kilonewton meter. Okay, and this happens approximately at a depth of say you can see that's 5 meters. So that's all for this tutorial. Thanks a lot for watching.